Good afternoon, everyone. My name is Peter Cutler. I'm based out of the UK. For those that haven't met me before, we're regular contributors to the UK Network Operators Forum, and it's fantastic to see such a great turnout at DKNOG. I think if your numbers increase like this, you might need a new location, so congratulations on that. I wasn't lucky enough to be here yesterday, but I was watching some of the core sessions on the live stream available on Vimeo, and just some context on where this technology update fits in the greater context of things. I think it was Marie's presentation was talking about her experience with SD-WAN implementations, and one of the icons on the early slides was security. So I'm going to try and cover one element of that very broad space from a software-defined orchestration piece of high-performance network edge nodes. But I'm also going to be tying that in with some core concepts that I've heard a lot about, and Julian talked about sort of feedback loops yesterday, and here we're going to be talking about how we can subscribe to our data streams to start to take telemetry from our edge network nodes to get feedback on security incidents in real time, rather than potentially waiting to time for that. So let's start with, we're going to start with a little bit about the threat landscape, talk about why the data that we collect drives the decisions we make on updating technologies in the industry. And then we're going to look at a technology update on what edge routing vendors are looking to, or are implementing in their technology that can help us mitigate DDoS at terabit scale. So this slide here represents probably the headline grabbers when it comes to denial of service incidents. And there's a clear trend over this time series data to what the headlines perceive to be the largest volumes of DDoS that hit networks and transit various large tier 1 ISPs towards their targets. Indeed, the latest Memcache event caused stir in the industry when Carrero came out and commented on at least technically, the ability to launch, shall we say, a kill switch from the sources of those attacks. At least that was technically possible. We know that botnets play a large part in initiating streams of traffic towards their targets. And perhaps as a suggestion, part of the reason that we haven't yet seen the latest and newest significant volumes of DDoS traffic in 2019, apart from it only being Q1, is that some of these botnets are being turned over to crypto mining and generating revenue for the actors behind those. So does this mean that DDoS in itself is going away? Well, no, not really. I think some key trends here are that IoT nodes are increasing in their numbers, and apart from perhaps endorsements from councils like the Information Security Council, there doesn't seem to be any slowdown in the volume of unsecured devices that are being released onto the market itself. Other trends that we're seeing include the sophistication of these attacks increasing, and some examples of those, as every attack vector is across a broad spectrum of methods in the security industry. But certain things are of a concern, and those include attacks that we might call spread spectrum, whereby you're no longer targeting just one victim, but you're targeting a large spectrum of IP addresses, which cause complications for traditional detection and redirection technologies, because of course the redirection of that traffic is now no longer to just one single victim, it's to vast swathes of perhaps cider blocks, which include vast amounts of good traffic, which can potentially be problematic in the movement of that across a core. We've also seen incidents of what we might call pulse wave, where you see very short, frequent spikes in traffic and reductions in those volumes of traffic. And that continues, and it confuses both operators and it confuses traditional monitoring systems. So let's stick to a data-driven approach to this. This is some data taken from Carrero's trend report, and the link is in the presentation here if you want to take a look at that. But just some highlights: 16% year-on-year increase in the average number of attacks across the customer base, 20%, 22% likelihood of attack if you are targeted once. But these two statistics in the middle here, these are the statistics that shape the technology development in the industry today. And essentially, we have a doubling of the number of attacks year on year that are over 10 gigabits per second. And the second of those is that these attacks are becoming shorter. And this poses the industry, at least the industry sector that I work in, a number of challenges. But in essence, the challenge is to, first of all, automate our current response to incidents and to be able to generate defense at enough scale to deal with the incidents that we're seeing across these networks. So if we examine a sort of a traditional approach to how we might solve this today, just for the purpose of a quick recap, really. This traditional, very conceptual architecture of an internet ISP peering, perhaps a subscriber edge with your core in the center here. What we've seen for a long time is that whilst that good traffic and some of that attack traffic transits these edge nodes, we've seen the repurposing of monitoring tools, which can be used for looking at AS path optimization and visibility into flows across the edge and across the core as well. We've seen the repurposing of NetFlow for monitoring to also detect denial of service. And in certain instances, that makes an awful lot of sense if you're looking for a basic increase in packet rate or bandwidth. And essentially what happens is once the attack traffic is detected, once those flows have been collected, once they are aggregated, exported to a flow collector, which deals with X number of volume in its deployment, we will then see BGP is then interacted with to announce the next path, the next hop, just like we heard in the excellent presentation from Marissa earlier, which is one of the options for BGP flow spec implementation. So typically, traditionally, you may send that traffic to what we might describe as a scrubbing center, or at least somewhere where that traffic could be dealt with that's heading to the destination in question. Now, one of the important design implications of this is that this is a slim fraction of your overall edge capacity. And the challenge that we face is that if the trend is towards attacks that are getting larger on average year on year, then there will be more occasions when the attacks are larger than our scrubbing capacity. And so we need to look at what options we have to us in that particular case. Often the result, which is free to everybody and implemented right across ISPs that I talk to, is the null routing of the destination or the implementation of remotely trigger black hole in BGP for what is hopefully a /32, but more often than not, it's actually a larger range of addresses. So let's look at the problem statement graphically here. This attempts to graphically represent the number of attacks that we see and the volume or the size of those attacks, but with two static lines on the chart. The first line is the peering edge capacity of the tier 1, tier 2, tier 3 ISPs. And in general, what we find when we speak to them is that they already have scrubbing centers or places where this attack traffic gets sent to, and that represents typically 10% of their edge capacity. And the rest of the options available to them for solving attacks that are larger than that capacity is, as we said, black hole, sometimes implementation of flow spec. So how can we propose to improve upon the amount of mitigation capacity that we can have? The work that we've been doing with Juniper specifically is a technology development which looks at in-silicon filtration. And one of the reasons I think the industry is moving in the right direction for this type of technique is a draft RFC amendment to flow spec, draft RFC 5575, which I would encourage you to look at. The extension to that talks about flexible payload matching on the router itself. So what if we can implement that today, and what if we can implement it in silicon? So what we're proposing is moving beyond traditional repurposing of monitoring using NetFlow, which is becoming increasingly difficult to detect attacks that are based on header tuple values, and moving towards a sampled mirror collection of data, which goes to an inspection engine, which can be a virtual function, typically within nodes like Marie was talking about yesterday, which will do DPI on those data packets that arrive, hopefully at the right speed and at the right performance as well. So in summary, what we're trying to do is enable software to define edge node operation where the scale exists to defeat these sorts of attacks, which is right at the very peering edge, where our provider edge capacity is at its peak, which gives us significantly more opportunity to remove large-scale incidents before we need to backhaul them across our network. So what would a model of this look like? And this is not any one specific implementation for any one vendor, but this is what we have deployed successfully in a tier 1 today. Model of software orchestration would look like implementing 3 separate features. Now, first of all, what we're ultimately trying to do is simplify the process. So this implementation with NetFlow, this interaction with BGP could, and is being significantly simplified by, first of all, taking a stream of monitoring from our edge nodes, which has a linear relationship to the ingress capacity. So essentially what we're saying is, we know that if we push 10 terabits ingress into our network, we know exactly what those monitoring amounts will be to our sampled mirror packet collectors. And that relationship is very important in a denial of service scenario, because being able to rely upon the collectors not becoming overwhelmed is very important. So this method also combines streaming telemetry as a feedback process, and we found that whilst the volumes of data are very low from telemetry features that can be streamed off edge nodes, the update process is also extremely fast. So you're no longer looking to poll using SNMP or poll specific counter values based on some Python script to work out whether or not, first of all, the attack is still there, or how that attack is actually progressing. So that closed loop processes can be very, very useful. And as a final component to that, we need an element that will react faster than BGP convergence, especially as the data tells us that the attacks are reducing in their time from the start to their finish. And the quick, instantaneous implementation of a line rate filter is the proposal to replace that mechanism. So going back to our original model, looking at full capacity mitigation, where the providers may have a place where packets can be scrubbed, what are we filling the gap with that will take us up to our edge transit capacity? Well, that gap is this area here. And using these sorts of methods, we can now scale to provide line rate firewall filtration at terabits. And this can be chosen for certain destination CIDR blocks. And of course, RTBH is always an option for you in any scenario. So the way that actually looks back on our basic concept is to take these sampled mirror packets, to send them to our collectors, which typically scale on a single commodity x86 bit of hardware that will ingest flows and payload data of the packets at rates that are typically very low. And once that attack arrives, we're looking to triage and implement defense right across the edge. So it doesn't matter which link it's coming in on, we want to implement defense before it has a chance to reach that scrubbing lane or indeed reach the downstream victim. And of course, this protects the network as well, because there's often a conflict of interest here. Some network providers, they want to protect their customers. Some network providers just want to protect their network. So it does depend on your priorities, but protecting the edge at terabit scale is definitely now an option, and all this happens automatically. So what do these filters end up actually looking like? There was some very interesting examples of those flow spec filters earlier. If we were to apply a filter here which would look at equivalent values that could be applied to family INET ingress interfaces, then the filter term has some details in it and then just a few actions which give us some feedback loop. And in this example here, what we're defining is the header tuple information, but what can also be added to this is flexible match masking, which you have to have the silicon to do on the router to be able to implement this, but we'll look for very, very specific payload values to make your application of filtration as accurate as feasibly possible so that there is minimal or zero collateral damage in that specific instance. Now this can be done, can be implemented manually upon request, or this can be implemented completely automatically. But the whole purpose of looking at software-defined orchestration of defense at the edge is that we take detection of the attack through to mitigation on the line cards down to about 1.6 to 2 seconds in time, which is a significant improvement. So just as a quick summary then, DDoS as a whole is still generally on the increase, and that trend report shows that data, which allows us to sculpt the way our product development and technology works. But what we're looking at as a technology provider is actually the abilities within high-performance routing vendors and edge nodes to perform this ability for us, which arguably is an essential place to mitigate DDoS traffic. And whilst RTBH null routing is an option available to everyone, typically there's been a lot of interest around the industry looking to perform these tasks on high performance routing vendor hardware. So typically this is a new opportunity, and this is going to cause a lot of discussion. So at this point, I'm happy to take your questions, please.
Hey, Marie from Global Connect. This might be obvious to everybody but the type of attacks that you would be protecting against, would that primarily be the volumetric attacks? Or would you also be able to mitigate some of the attacks that target the higher application layer? Yeah,
thanks for your question, Marie. There's a clear space where this technology clearly makes sense, and that is volume. Now, attacks that don't threaten the availability of your network or your services, those are best served by looking at different, perhaps DPI technologies, either off-ramped or further closer to the network. So this is definitely protection of the network from a volumetric perspective. Thank you.
Hi, thanks for the presentation. This is the second period to present in the afternoon.
Yeah.
The Lung came first, and now you. I have a PhD thesis cleverly disguised as a question.
Okay.
It's sort of following up on this question that we just had. In a sense, the volumetric attacks, they hurt. I mean, they saturate bandwidth, they do all kinds of things. They might stop access to a particular server or an ISP. But the more subtle attacks, especially in this age of a lot more traffic being encrypted, how do you stop those? How do you even detect those? And where I'm trying to steer this is, are there techniques in AI and machine learning? And I'm sorry if I'm going way off your subject, because it's not about terabits anymore. It's about people trying to, subvert things, but without getting detected. Are there ways that we can use techniques from machine learning, maybe, or other techniques, to detect these kinds of things and find us protection, even though these guys are, like you said, they're the pulse attacks and things that are not just blasting things at you, but trying to sort of stay under the radar. Can you sort of expose them anyway? Are there techniques that are being pursued to do this?
Okay, that was reasonably big question. So let's look at typically how the industry as a whole has approached this problem. So there are various methods from a volumetric perspective. This one specifically, BGP flow spec implementations, RTBH, which look at volume. And across the spectrum, they have trade-offs where you trade off accuracy for typically the cost of implementation as well. Now, when the attack types are becoming more sophisticated and perhaps don't threaten the availability of the network through volume, the approach that I've seen that's been taken is to offload some of those packets onto UTM-type technologies like load balancers, where SSL decryption is an option, is a line card add-in, or perhaps individual ASIC-based technologies or x86 technologies can inspect those packets in more detail, where the volumes are appropriate enough that don't cause input queues and technologies that rely upon a pipeline type architecture to be able to inspect that appropriately. Now, one of the things I think the industry has struggled with is two approaches to doing that when the volume is low. And one approach is to use rudimentary thresholds for blocking traffic. But again, it's that trade-off of accuracy versus allowing the traffic through. The other approach is to work out with technologies like machine learning that are implemented in many different guises, both open sources and closed source in using things like Splunk, is to look at what the exact attack vector is. And if you can try to work out what the method of sending those packets are and what the method of the attack is and what those attack packets exactly look like, then you are going a long way to solving the problem in completeness at a lower volume level. So I welcome more discussion on that. Thanks for your question. Okay.
Any other questions? No? Then thank you very much, Peter.
Thank you.